First, we have Esty Kelman telling us about new proof for the KKL, Friedgut, and Talagrand theorems.
Okay, thank you. Okay, so this is joint work with Subhash, Khot, Kindler, Minzer, and my advisor Muli, Safra. I bold here the KKL because that's what we can see in this short talk. So let's start with some basics. Oops, what I did. Okay, so a Boolean function over the binary hypercube. So for every n, we can think about the n-dimensional binary hypercube, which is just a graph constituting of 2 to the n nodes. Each one is n tuple of 0 and 1 bits. You can see as an example for 3. The edges are between every 2 nodes that differ in exactly 1 coordinate. And the Boolean function is a function of n input bit and 1 output bit. We can think about it as just 2 coloring of the n of the binary hypercube. And we have 2 types of edges. There are the monochromatic edges, and the others are the influential edges. There are sensitive edges. We can call them sensitive edges. They are the edges that are going between 2 different values of the function. And we can restrict our view to one specific direction, say direction I, and then we ask how many sensitive edges we have in this direction. The fraction of these edges over all the edges in direction I is the influence of the variable I. This is just the probability over a uniformly random input that flipping the ith bit changes the value of the function. We can sum up all of them together to get and this is called the total influence. This takes into account all the sensitive edges in all over the cube, in all direction, and therefore it's equals to the number of sensitive edges in the entire cube normalized to 2 to the n minus 1, and that's why it's also called average sensitivity. The total influence and the influences are very important properties of Boolean functions, and basic questions in this area related to it. We can ask, what can we say about the structure of a function if we know that the total influence is small? For example, if we know that the balanced Boolean function as total influence equals exactly 1, we know that this is a dictatorship. This is not hard to see. And other basic classic results are the KKL type results, which we are talking about. So what we do is we give a unified approach, a new proof for these 3 results. The KKL theorem, which says that for every balanced Boolean function, either there exists a variable with a large influence or the total influence is large. We say that actually every Boolean function can't have both the total influence very small and all the individual influences small. The Friedgut theorem say that those functions with small total influence essentially depends on very few variables. And Talagrand's inequality is a generalization of the KKL. And in the original proofs of all these 3 theorems, there is a common key technique they used, which is the hypercontractive inequality. And this inequality is considered a bit mystery how it works, and it has some limitations, which are not elaborate now. We have it in the long talk. What we do is to give a new proof, and the tools we use is random restriction in a very certain way. What we try to do is to take in the random restriction to take the Fourier mass of the high levels and put it to the low levels, and then we get the total influence small, and the structure is a bit simpler. And on top of this, we apply the Log-Sobolev inequality which in some sense take the place of the hypercontractive inequality. So what we will see in the few minutes we have, I'll try to cover the idea of the proof for the KKL without all the analysis we do to the Log-Sobolev inequality. But I guess we can see something of it. So let's start with the random restriction. For this, we need a bit about the Fourier analysis. A nice fact about functions over the binary hypercube, even those that go to the reals, every function has a unique representation, which called the Fourier representation, and looks like this. This is the summation over all subsets of variables, f at s times chi s of x, where chi s of x is the character function. What's important about it is that this function considers only the variables in the set S, and f at s is the Fourier coefficient of the character S. This is the real number. And now we can define the degree of a function. We can see what is the character which has a non-zero, the largest character that has non-zero Fourier coefficient. And a nice fact about it is if we think about a homogeneous function, which is a function that all the characters which are not of size d as the Fourier coefficient which is 0, then for these functions, if it's Boolean function, the total influence equals d, the degree of the function. And now we can do random restriction on these functions. And we have a function with n variables. We want to have some subset of these variables to stay alive. We choose a set J of the variables to stay alive with some probability mu. Every variable will be contained in J. And for the other variables, we want to fix them. So we choose the assignment for the other variables randomly, 0 with probability half and 1 with probability half. And this way we get a random function. It's each J, the set of alive variables, and assignment fixing for the other variables define a function which its values are the values of a subcube of F. And now we can ask some questions about this random function. For example, we can know that for every, if we choose mu to be 1 over d, for every character subset of the variables of size d, the number of alive variables that will stay alive is expectedly 1. So now I guess that I can do it in 1 minute. The proof idea of for the KKL, we want to show that if all the individual influences are small, then the total influence is large. So we can think about a homogeneous function of degree d and do 1 over d random restriction. Then all the weight is on degree 1. And then we know that every restricted function is actually a dictatorship. That means that each restriction z choose some j to be the dictatorship. Now we can partition all the z's in the cube according to the dictatorship they choose. So we set a set aj is all the z's that choose each j to be their dictatorship, and we can ask how large is this set. So we can see that if z is in aj, then xj is the dictatorship there, and therefore it's influential. Going in direction j will change the function, the value of the function, and for every z that is not in xj, let's say in al, then xl is the dictatorship there, and therefore xj is not influential there. And therefore, the density of aj is exactly the influence of the j's variable. And now we assume that all the influences are small, therefore also the density of aj is small. So now we need to find another place in sensitive edges. So look at an edge that is in between two sets. We can see that this edge is going from one dictatorship to other dictatorship, and therefore this edge is sensitive. So now we can just count all of these edges, and we can see that there are many edges in between the sets. And here we use the edge isoperimetric inequality that we can use only here in this case. It's just a corollary of the Log-Sobolev inequality and says that we have many edges going from inside a small set to outside it. We can sum up all of them together to get that we have large average sensitivity, which is a total influence. And this is the idea of the proof. We need more analyze because not everything looks just so perfect that we have exactly what we want. So we'll not do summary, it's the same. About open questions, we hope that this new techniques helps find more statements and even prove known results. Thank you.
Thank you. Okay, I guess we have time for maybe a quick question while Tselil sets up.
You have a question? Where can I see it?
Feel free to unmute yourself and ask a question. So maybe one question that comes to mind. You mentioned all these famous inequalities, but one of them that I noticed was missing is the FKN inequality, which is sort of like a version of Friedgut for level 1. Do you think that it can be proved using these techniques, or have you tried?
Prove it? Actually, I used it when I said that, yeah. I don't know what to tell you to answer about it.
So you used it as part of the KKL, you were saying, or?
No, when I say that that I have all the weight on the first Fourier level, and then the function is dictatorship, it's not actually true. I need the FKN now.
I see. Okay. All right. All right. So maybe let's move on to the next speaker.
I can't share my screen unless Esty stops sharing her screen.
Should I stop?
Yes. I also remind you that we have longer versions of the talks and the conference website. So if you want to see more details, you can check it out. And feel free to stay around for the discussion and ask questions later. Okay. Still? Can you share a screen?
Yeah, I'm trying. Okay. All right. So everyone can see my screen?
Yes.
Okay. Great.
It's
so
too big, I think.
It's too big. Yeah, for some reason, Zoom isn't letting me share the window like I planned.
Yeah.
So it's forcing me to share the whole screen. No, it's probably too small. Yeah, I'm not sure what to do.
You want to stop the share and then try starting it again?
Yeah, sure. Yeah, it doesn't seem to give me an alternative except for sharing the whole screen.
Maybe you can try again with the whole screen, and I mean,
Okay.
you can play with the size of the window a bit, and then.
Okay. So I mean, I don't know what you guys see, so.
So now it's again too big. So if you can make it a bit smaller, then we can see the entire slide.
Can you see the slide?
Can you fill the first quadrant of your screen, with the window? Yeah.
Looks good now.
That's pretty good.
Okay. All right. Sorry about this. So I guess, should I start?
Yeah.
Okay, so this talk is about something which we call the Strongish planted clique hypothesis and its consequences. And this is based on joint work with Pasin, Manurangsi, and Aviad Rubinstein. So let's start. So the topic of this talk is the planted clique problem, in which we have to distinguish between the following two graphs. So either with a graph sampled from G and half, which is the uniform distribution over n vertex graphs, or alternatively, you can think of it as I have n vertices, and then I sample each edge to be in the graph independently with probability half. My other distribution on graphs is I will sample a graph from G and half, and then I'll choose a random subset of k vertices, and I'll put a clique on it. And my goal is, given a sample from one of these two distributions, to decide which distribution it came from with high probability. Okay, so because the size of the largest clique in G and half concentrates really well around 2 log n, there's a trivial algorithm running in quasi-polynomial time. Basically, you just run brute force search over all cliques of size slightly larger than 2 times log n. In terms of efficient algorithms, the size of the clique that we need in the planted distribution in order for the problem to be solved in polynomial time is root n. So this is the best algorithm that we know. It's a spectral algorithm due to Alon, Krivolevich, and Sudakov. And the planted clique hypothesis states that for any clique size that's less than square root n asymptotically, the planted clique problem is not solvable in polynomial time. And this hypothesis has been used in several hardness results. So assuming that the planted clique hypothesis, you can get an approximability of densest K subgraph, hardness for finding the best Nash equilibrium, hardness of sparse PCA, and several other average case problems. So this is a kind of popular hypothesis. And the main contribution of our work is to introduce something that we call the Strongish planted clique hypothesis. So this is a stronger version of the planted clique hypothesis, which states that as long as the size of the planted clique, kappa, is less than n to the 0.1, or there you can replace it by any fixed constant less than half, the planted clique problem is not solvable in n to the little o of log n time. Okay, and we call it the Strongish planted clique hypothesis in sort of a homage to the strong exponential time hypothesis, except for here we don't require that the constant in front of the log n is fixed to 2. So it's kind of like an exponential time hypothesis for SAT, but for planted clique. Okay, so why would we make such a hypothesis? Well, it's supported by lower bounds for large classes of algorithms. So for example, there's a sum of squares lower bound due to Barak et al. And also similar lower bounds for statistical query algorithms, although here you have to squint your eyes a little bit in order to accept that these prove such lower bounds. So in any case, this rules out many known algorithms. And so if there's an algorithm that beats n to the log n time, it would need to be pretty different than any algorithm that we currently know. Okay, so after introducing the Strongish planted clique hypothesis, we're able to derive several tight hardness results for other problems. So on the one hand, we have tight inapproximability results. And on the other hand, we have tight running time lower bounds. So our first inapproximability result is that we show that there's no polynomial time algorithm, which gives a better than k approximation factor for the densest k subgraph problem. And it's easy to see that this is tight because to get a factor k approximation algorithm, I can just output a single vertex. And then using a bunch of known reductions in the literature, we get tight inapproximability results for several other problems, including smallest k edge subgraph, Steiner k forest, directed Steiner network, and densest k subhypergraph. Okay. So on the other side, we also get tight running time lower bounds. So here we're able to show that there's no n to the little o k time algorithm that gets a constant approximation for densest k subgraph. And here it's also easy to see that it's tight because if you're looking for a subgraph with size k, you can do brute force search over size k subgraphs in n to the k time. Okay, so this then yields, again, using pretty simple reductions, we can get tight running time lower bounds for the pattern detection problem. So in pattern detection, there's two versions of the problem. There's where you're looking for an induced graph or non-induced graph. So we can get that there's no n to the little ok time algorithm for any k vertex induced pattern detection problem, and no n to the order k time algorithm for almost every k vertex non-induced pattern detection question. So these are the sort of first tight running time lower bounds for all of these problems, albeit we start with the Strongish planted clique hypothesis, which is a stronger hypothesis than has been used before. Oh, and I should mention that all these results also hold for fixed parameter tractable algorithms as well. Okay, so I have 2 minutes left, so I'll do my best to give you a taste of the proof, but I might just cut to the end in order to spare you, and you can watch Pasin's nice 25-minute version for more details. So both of these main results about densest k subgraph are proven by using the same reduction and just plugging in different parameters. So here, I don't want you to take anything away from the slide except for that we're using the same reduction. There's going to be some parameters k, l, and n, which will become clear on the next slide, and we just choose different values of l to get the two different theorems. Okay, so our reduction is going to exploit the randomized graph product, which has been used many times before in hardness approximation reductions. The randomized graph product is defined as follows. We start with some graph. This is going to be the graph, which is our planted clique instance. And then we choose parameters k, l, and n. And what we do is we're going to pick random subsets, capital N random subsets, each of size L vertices in G. And we're going to make one vertex in G prime for each subset. And then we'll add an edge between the vertices corresponding to those subsets in G prime if the union of those vertex sets is a clique in the original graph. So here, for example, I may have chosen S1 to be V2, V3, S2 to be V1, V2, S3 to be V3, V5. And then I can look and I can see that the union of S1 and S2 in the original graph is not a clique, so I don't put an edge there. The union of S1 and S3 is a clique, so I do put an edge there, etc. Okay, so I'm at the 8-minute mark, but the complete distance soundness arguments are both quite simple, though they do require some non-obvious, analysis. And basically, we use the fact that the random choices of the subsets form a disperser in the original graph. All right, that's it. So, so quickly concluding, so we propose this Strongish planted clique hypothesis, and we're able to get tight inapproximability results for several problems, tight running time lower bounds for several problems. Future research directions. It would be really nice to get inapproximability results where the k depends on n, so we can't get this with our techniques. are there more applications of this Strongish blended clique hypothesis? Can we prove the same tight hardness results under different assumptions? Thanks.
Thank you. Okay, great. So I have a bunch of questions, but I can also save them for later. Anyone who wants to ask a question, feel free to unmute yourself. So one question is, the reduction is randomized, right? So therefore, you need to sort of base your assumption on no randomized algorithm for planted clique, right? So is there any hope to do it with deterministic algorithms, or their equivalent conjectures?
It may be possible to use some pseudo-randomness instead, because the property that we use is that the sets will kind of form a disperser. But I guess we didn't think about it, so I'm not sure.
Okay. Right. So I guess let's thank Tselil again. And next we have Omri.
Yeah. I share my screen now.
Yeah. Okay, good. Seems to work.
Great.
Okay, so Omri Ben-Eliezer would tell us about limits of order graphs and their applications.
Thank you, Avishai. This is joint work with Eldar Fischer, Amit Levy, and Yuichi Yoshida. So in this talk, I will discuss limits of graph sequences. This is an analytic perspective on graph theory, where we employ analytical terminology and tools to study very large graphs. And this has various motivations and applications. For example, in property testing and extreme combinatorics, there are many results that are much more natural and easier to prove using graph limits. And I will mention some examples. As another example, in probability or statistics, limits of graphs are useful non-parametric model to represent natural distributions over large graphs. For example, of social networks or interaction graphs in statistical physics. Typically, one is interested in sequences of larger and larger graphs that have some common characteristics. And the limit object, the graphon, represents these characteristics in a unified way. Since the graph limit theory was established about 15 years ago, various types of limits for combinatorial structures have been developed. Here are just a few representative works. And in our work, we develop a limit theory for ordered graphs. So we consider graphs whose vertices have an underlying ordering. For example, you can think of an image as an ordered bipartite graph, where one part corresponds to the rows of the rows in the image, the other part corresponds to the columns. And the edge color between row I and column J, so it's an edge colored graph. And the edge color between row I and column J corresponds to the pixel color in the location ij. Other examples of naturally ordered graphs include the temporal graphs, where vertices are ordered by time, and geometric or location-based graphs, where vertices are ordered by location. A sequence of unordered graphs is considered convergent if the density of any finite substructure converges among graphs in the sequence. For example, a sequence of Erdos-Renyi random graphs, GN1/2, converges with probability 1, because the subgraph densities converge with probability 1. An equivalent and more useful notion of convergence is via the cut distance for graphs, which is defined here on the right. And the space of graphons has many desirable properties. It is complete. It is also even compact. Graphons allow sampling, and the subgraph densities are the limiting densities of the corresponding graph sequence. And like unordered graphs, the representation is symmetric. So it is invariant under measure-preserving transformations, which is the same as saying for graphs that the representation is invariant under running a permutation over the vertices. Okay, so one first may ask whether we can use the cut distance that we used for unordered graphs, whether we can use it to define convergence for ordered graphs. And the answer turns out negative, both when we allow measure-preserving transformations like in unordered graphs, and also when we do not allow them in hope to preserve the ordering of the vertices. So there are some counterexamples here. I explain them in more detail in the longer talk. But our first contribution in this work is to develop a new variant of the cut distance, which we call the cut shift distance, which correctly captures convergence of ordered subgraph densities. The distance function allows making measure-preserving transformations, but we have to pay for them if we want to change the order of the vertices. So it allows us some flexibility that we need for the distance function to be expressive enough, but we don't allow too much expressivity. So the ordering of the vertices will still make sense in the limit object. However, a graphon, so we could try to use graphons with the cut shift distance, but the graphon is not a sufficiently expressive limit object, even if we couple it with the cut shift distance. So not only that we need a new distance notion, we also need some more expressive limit object. And the limit object we devise is called an orderon. It is 4-dimensional rather than 2-dimensional, as is the case for graphons. And this is because we need to represent each vertex by 2 coordinates. One that describes its location in the linear ordering, and then another one that provides some sense of expressivity. And finally, orderons with the cut shift distance are sufficient to develop a limit theory for ordered graphs. So, and we proved several results that constitute this kind of limit theory. These are completeness and compactness theorems that show that the space of orderons satisfies these properties. A sampling theorem that characterizes how finite ordered graphs can be probabilistically generated from orderons, and also a theorem that shows that finite ordered graphs are dense in the space of orderons. Perhaps the most interesting main result is a pixelization lemma, which roughly states that any orderon is closed in L1, or if you prefer, Hamming distance to a finite description orderon that additionally does not contain any like noisy features that did not appear in the original orderon. And this is kind of a useful analytic form of semi-ordered regularity for ordered graphs. We give 2 applications to demonstrate the usefulness of our limit object. One is a new proof of the ordered graph removal lemma. The proof is much simpler than the known combinatorial proof that we previously had, and it exemplifies why the analytic perspective is sometimes the most natural one and the easiest to use one. The other result is a new result in experiment combinatorics. It shows that asymptotically the furthest away graph so for any hereditary property of ordered graphs, there is some ordered stochastic block model, so that generating graphs according to this stochastic block model will generate graphs that are almost the furthest away from the property. And this is a generalization of a beautiful result by Alon and Stav, which also I think the proof was using graph limits. And for some future directions, so we mostly investigated this limit object in a combinatorial context. The applications that we provide are combinatorial, and it would be interesting to study orderons as a generative probabilistic model for ordered graphs. And obviously it will also be interesting to, so our limit object is for dense ordered graphs, and it would be interesting to understand limit objects for other ordered graphs, for example, limits that are for sparse graphs, or image limits that are more natural. I mean, our limits are not really natural for images. Okay, thank you.
Thank you. Okay, great. So maybe we should transition to the next speaker, and meanwhile, feel free to ask questions. So next we have Vinayak.
Oh, yeah.
Yeah. So you know, Omri, I'm curious. How did you decided to go from this 2D graphon model to this 4D? I mean, why was it the natural choice?
So it just seems that the 2D is not enough. I mean, we've seen some concrete measure theoretic reasons why graphons are just not expressive enough. There was this example of the odd clique example that you might have seen on one of the slides. So this is an example of a sequence of ordered graphs that do seem to they need to converge. I mean, the subgraph densities converge, but they don't seem to have any reasonable limit object as a graphon, and this could be actually proved. It just seems that you need more expressivity. So we use another coordinate for this expressivity, and in fact, there was an independent work on Latin squares, generalizations of permutations, and this is also a 2D object, and they also seem to use a 4-dimensional limit object. So I don't have any concrete bound showing that it's not 2-dimensional, because we need to define what 2-dimensional is, but it seems to not be 2-dimensional.
Okay, thank you. Okay, I guess we're short on time, so let's go on to the next talk. So this is about the pseudo-binomiality of the sticky random walk, and presenting the work would be Vinayak Kumar.
All right, yeah, I'm Vinayak, and today I'll be presenting joint work with Venkat Guruswamy, and I'll be talking about the pseudo-binomiality of the sticky random walk. All right, so our project is basically considering statistical properties of the expander random walk. So let me first describe an expander. So an expander, expanders are deregular graphs where you think of the degree as like small in terms of the number of vertices. And it's defined based off of its normalized adjacency matrix. So if all of its non-trivial eigenvalues is bounded in magnitude by some constant less than 1, we call it a spectral expander. And random walks on expanders are very useful in pseudorandomness. They're used a lot in constructing pseudorandom objects like generators, extractors, error correcting codes, or error amplification protocols. And so a natural question to ask is what pseudorandom statistical properties do expander walks have? And this is a question that we surprisingly know little about. And so we hope to answer this. So a particular model of an expander walk we look at is one where we have an expander graph and then we mark half of its vertices. And we look at a bit string distribution where we do a random walk and then we look at the string, the indicator string, which indicates which step was on a marked node. So for example, if we have a random walk here, you can verify that this is the bit string corresponding to it, since like the first step is not marked, the second and third steps are marked, and so on. And what we focus on is the total number of visits to a marked node, which is equivalent to looking at the number of ones in the string or the Hamming weight of the string. So there has been some results on this number. For example, using Chernoff arguments, it's been shown that the number of visits is concentrated about n/2. And more recently, it's been shown the parity bias of this number is exponentially small. So it's like odd and even with almost the same probability. And this led to a breakthrough construction of epsilon balanced codes. So in general, what we're trying to do is we're looking at the pseudo-binomiality of this number. And it basically, how close is this distribution to the binomial distribution? And we chose the binomial distribution because it's the distribution of the Hamming weight of a string. And as a modest step in this direction, we analyze what we call the sticky random walk, which is a necessary proxy towards understanding the general expander walk. So the sticky random walk is the following. We have two parameters. N is the number of steps, and lambda you can think of as the stickiness factor, which will serve as the proxy for the expander's second largest eigenvalue. And the distribution is defined where the first bit is 0 or 1 with equal probability. And then every subsequent bit will stick to the current bit with probability 1 plus lambda over 2. And then we'll swap to the other bit with probability 1 minus lambda over 2. So it can be shown that the sticky walk is necessary to understanding the expander walk because it basically it represents a specific class of expander walks with second largest eigenvalue lambda and half of its vertices marked. So this is basically a special case of the general expander walk. So a main result we prove is total variation distance bound. So let S be a sticky random walk bit string, and then let T be a purely random string. We show that the total variation distance between the distribution of these Hamming weights is theta of lambda. And so, of course, TVD is bounded by 1. It's interesting to see as lambda goes to 0, like we see the exact decay. And the tightness of this bound we show is realized by the event where we shift everything to the plus or minus 1 version of the walk. And the event that the Hamming weight is at most the square root of the number of steps gives our omega of lambda separation. So in order to prove the upper bound, what we use is some Fourier analysis over the Krautchuk functions. And we choose the Krautchuk functions because their inner product is defined based off of the binomial expectation. And so it turns out this is very useful in analyzing how close this distribution is to the binomial distribution. So if you work with it, you sort of see that the 0th coefficient represents how binomial it is. And then the remaining coefficients basically show how much it deviates from it. So in spirit, we're basically need to sufficiently upper bound these remaining coefficients, which turns out to be this expression. And bounding this by O of lambda is essentially how we go about this. And there's some exciting recent work by Cohen, Perry, and Tashma, just like the end of 2020, where they show a TVD bound of lambda times some polylog factor between the Hamming weight of the general expander walk and the Hamming weight of a purely random string. And their approach is quite similar, but they had to be more careful in computing the expectation of the Krautchuk function of the expander indicator bit string rather than just a sticky bit string. And as an example of how much we don't know about this of this sticky walk, we have two results, right? So we have one result from Chernoff saying, from Chernoff bound saying that the number of visits is very close to the mean, and we have another saying the parity is the parity bias is very small. So what if we asked, oh, what's the probability? What's the probability the number of visits is at least n/2 and it's even? Or like, what if it's less than n/2 or odd? So even these events, they're unknown. And so as a modest step towards answering these questions, we look at this question in the sticky walk setting. And so as another result, we show that the majority and parity bit are almost uncorrelated by showing like in all of these 4 cases, the probability is 1/4 plus some little o of 1 factor. And the proof idea, it does depend quite a bit on symmetry. And in the cases where, like the middle case where the symmetry doesn't handle, we use Krautchuk functions in order to upper bound this central probability coefficient to be our little o of 1 factor. So some future directions would be, we almost have it, but can we establish O of lambda factor for the general expander walk setting? So basically, can we remove that polylog factor from the distance? And then, as I said, we did depend on the symmetry of the sticky walk in order to show the parity and majority result. So is there a way to replace this symmetry part with some Fourier analysis so that we could perhaps generalize it to the expander walk setting? And then finally, is there a way to essentially reduce more cases, more events from the expander walk to the sticky walk? So there are moment generating function results that say that you can you can reduce, you can lift bounds on monotone functions from a biased version of the sticky walk to the general expander walk. But how about like non-monotone functions like parity? Is there some way we can show some relationship between the expander walk and the sticky walk? And so thank you for listening, and that's what I have.
Thank you. Since we're short on time, let's move on to the next speaker and keep the question for later, for after the last talk. Okay, so next we have Dor, I believe.
Yes, that's true.
I saw both you and Mark, so I was uncertain a bit, but yeah.
Yeah.
Okay.
So can you can hear me, right?
Yeah, we can see your slides as well.
Good, very good.
Okay.
Yeah.
Good. So Dor Minzer would tell us on rich 2-to-1 games.
Thank you, Avishai. So hi, everybody. Thank you for sticking to the end of this session. So I'm going to talk about rich 2-to-1 games, but before I do that, let me give you some background of what we're talking about. So this is joint work with Mark Braverman and Subhash Khot. So it all starts, of course, with the PCP theorem. And to formulate it, let me define the label cover problem. So here is a formulation, but basically what is a label cover? You have a bunch of constraints, which are described by a bipartite graph. You're supposed to give labels to each one of the vertices, and you want to satisfy the constraints that are on the edges. Simple enough. And the goal, of course, is to satisfy as many of the constraints as possible. So in this language, you can state the PCP theorem as follows. There exists some delta less than 1, and k, which is the alphabet, a bound on the alphabet sizes, such that if I give you a label cover instance, it's NP hard for you to tell me whether you can satisfy all of the constraints or at most delta of them. Okay, so this is the most vanilla basic PCP theorem, and it's very nice. You can do a bunch of stuff with it, but often it's too weak to derive like optimally inapproximability results, or sometimes any inapproximability result at all. So people look for stronger versions of this theorem, and there are sort of 2 main avenues for that. So first of all, you can ask to improve soundness. You can ask to reduce this delta. And this is something that I'm not going to talk about at all. This is, if you heard the name parallel repetition theorem, this is what this is all about, and it's very good, it's very useful, but not for this talk. This talk is more about the second point, which is obtaining more strict structure on the constraints of the problem. So this is this talk. Okay, so we want a better structure for the constraints. So what is the best structure you can hope for? What is the ultimate structure? Well, this is what we call unigames. So what is a unigame? It's a specific instance of label cover wherein the two alphabet sizes are the same, and each constraint is as simple as it gets. It's a one-to-one map. Okay, so for example, maybe the alphabet is a field, and the constraints are equations, linear equations in two variables. So, so this is what unigames, and a conjecture by Subhash Khot is that label cover remains hard on unigames. More precisely, for all delta greater than 0, for large enough alphabet, it's NPR to tell whether a given unigame is almost satisfiable or at most delta satisfiable. So this is the conjecture, and of course, because it is a conjecture, there are pros and cons of it. So the pro is that if you're willing to assume that, you get a bunch of results, you get many implications. But of course, the con is this is a conjecture, so whatever we base on it may collapse if the conjecture fails. Good, so let's try maybe something a bit weaker. Let's try a near ultimate structure. So what number comes after 1? 2. So instead of unigames, we talk about 2-to-1 games. It's basically the same, except that now each constraint is a 2-to-1 map and not a 1-to-1 map. In the same paper, Subhash Khot conjectured that this problem is also hard, basically the same hardness as of unigames. But now comes a bit of a difference. So now, basically, we know that this conjecture is true. We know that this is NP hard. We know that 2-to-1 games is NP hard. So this is a pro, right? This is not a conjecture, it's provable. But what is the con? Well, less applications, right? You have to pay for something. And the main question that we consider in this work is, are there any intermediate problems between 2-to-1 games and unigames? Okay, so for that, I'm going to define, this is going to be a bit more technical, but I'm going to define basically a new parameter of label cover problems, and this is what will determine our intermediate problems. So let's fix a 2-to-1 game, psi, and now I'm going to define the richness parameter. So for that, first, I'm going to associate a partition of the alphabet for each vertex and a neighbor of it. So let's fix a vertex U on the side with the larger alphabet, on L. And now let's consider each neighbor V of U. I claim that the neighbor V of U naturally induces a partition of the alphabet of U. So why is that? For each symbol that V may get, there are two symbols that U may get so that the edge is satisfied. So this inverse map defines to you a partition of sigma L to sets of size 2. And this is what is written here. This is the partition that U and V define. Good. So now that we define that, we can associate with each vertex a distribution over partitions. So for each vertex U, you sample a neighbor V uniformly at random, and you output the partition that U and V define. And intuitively, the richness parameter measures how random looking this partition looks like. So let's be a bit more formal, but Right? Don't take it too seriously. You can look at the longer version of the talk if you want to get more serious. But basically, the more random looking this partition is, the greater the richness is. And roughly speaking, you sample this neighbor V, you look at R samples of pairs. If they look random, then you call it R-wise rich. And the larger R is, the happier we are. And if R is the whole thing, if everything looks completely random, then we call the game fully rich, or just rich. We'll drop the fully. So now this is sort of the main definition that we have in this work. And this property raises several questions. What can you say about these problems, and how do they relate to unique games and two-to-one games? So let me state the two conjectures that we make in this paper. So the first conjecture asserts that if I give you a fully rich two-to-one game, it's NPR to tell whether it's almost fully satisfiable or at most epsilon satisfiable. But note that here, unlike unique games, there is no reason to believe that satisfiable instances are easy. So this is our second conjecture. We conjecture that even on satisfiable instances, it's still NPR to tell whether it's satisfiable or at most epsilon satisfiable. So these are the two conjectures that we make. And two very natural questions is, how are these conjectures related to unique games? And secondly, why study them? Of course. So the main sort of result that we prove in this paper is that the first conjecture is actually equivalent to unique games. It's completely equivalent to UGC. And one direction is easy. If you assume unique games, it's very easy to reduce it to rich two-to-one games. The other direction is more tricky, and this is where most of our effort goes. I should mention that the reduction itself is standard. It's a reduction from a paper by Kindler et al. But actually, to do the soundness, we have to use some new analytical tools, and in particular, some hypercontractive inequality on the symmetry group. Good. But now that we know that conjecture 1 is equivalent to UGC, it raises the question of what about conjecture 2? Because clearly, conjecture 2 is stronger than conjecture 1. So what can you say about it? And what I sort of want to argue is that this is sort of a version of unique games with perfect completeness, but one that is plausibly hard. And I find it very, very interesting. And like in the next slide, I'm going to basically tell you what I think about it. But this is sort of the main message that our work gives, that there is this ladder of problems that we want to study that eventually will lead us maybe to unique games, but there is even a stronger conjecture that may have greater implications. Yeah, so this is sort of the last slide of my talk. So this is what I said. So here are some open directions. So it's easy to show that if you assume the R-rich conjecture for R equals 1, actually it's not an assumption because it is true for R equals 1, you get that unique games between half and epsilon is NP harder. And if you assume full richness, then our main result says that you get the whole thing. So an interesting question is, what would you get if you prove that 4 rich games are NP harder? Would you get something better than half? So my feeling is that the answer should be yes, but we don't know. And secondly, and this is sort of the point that I tried to deliver on the last slide, now that we have some conjecture that is stronger than UGC, and it's plausible and has perfect completeness, we can hope to use it to prove hardness for satisfiable instances. So there is a very nice result by Raghavendra that uses UGC in order to prove some dichotomy for the entire class of CSPs. But because of this imperfect completeness, it doesn't apply for satisfiable CSPs. So I have some hope that we may be able to prove analogs of this result, but yeah, this is a long road, and so far we only have some preliminary results in a work in progress. And finally, this is sort of a more moral question, but there is this object called the Grassmann graph, which is used to prove hardness of standard 2 to 1, which, as I said, is the same as R-reach for R equals 1. Can we find some combinatorial gadget that will hopefully give us, or plausibly give us, hardness for R-reach games? So I think that even coming up with some candidate would be very interesting, but so far we don't know of anything that is too promising. So that's all I have. Thank you for listening.
Thank you. Okay, so I think we are now, we should start the discussion now, and I invite you all to ask questions and open with the floor to ask questions for any of the 5 speakers for giving us these great talks.
Hey.
Go.
Jay?
Oh, go ahead, sorry.
So I had a question for the pseudobinomiality talk. Is there any aspect in which we know that the expander walk differs from the sticky walk, or as far as we know, they behave very similarly in terms of anything I might want to do?
Like, what do you mean by differ? I get like there are some, like the sticky walk can be simulated by like some like expander walks, like the set, like the sticky walk over like lambda will like simulate like only a certain only like certain expanders, but it's not known for like arbitrary expanders, like what really the relationship is. With like we know like moment generating function like upper bounds and even in that case it's upper bounded by a slightly more general version of the sticky walk, like a biased version. So there's no like it. I think it's more like folklore that like, oh, if I have a marked expander, I can sort of think of it as a sticky walk type of thing, but there aren't many concrete results that bridge the two together.
Thanks.
Thank you.
I had a question about the ordered graph in this talk, I think to Omri. I was wondering if you could say a little bit more about why the cut distance, why you have to use this like cut shift distance rather than the cut distance.
Yeah, so the cut distance usually, so there is the cut norm that where you can compare 2 graphs, but you don't allow reordering of their vertices. And so the cut norm, if you don't allow reordering, there are some examples where it is just not expressive enough. So basically you want subgraph density. So you want that if a sequence of ordered graphs is convergent in terms of subgraph densities, then it will also be convergent in the distance norm that we use. But in the cut norm, this example doesn't converge. So it just seems that if you allowed a little bit of flexibility, then this example, so this example is, we call it the odd clique example. So you take a graph on n vertices, where an ordered graph on n vertices, where all the odd vertices are connected to each other, and that's it, no other edges. So it seems that if you can slightly reorder the vertices, then they become the same, and then the cut norm between them will become 0. But if you do not allow reordering, the cut norm is very large. On the other hand, if you allow transformations, if you allow permutations over the ordering, then you just lose the order. So you need some flexibility, but not too much. So and this is what we provide.
Okay, that makes sense. Thank you.
Yes.
I had another question.
Yeah. Go ahead.
No, go ahead, Aviad. Okay, sure. Vinayak, I was wondering, I know there's work on like, I think they're called edge-reinforced random walks on graphs, which I think you did, Diaconis and collaborators. And I was wondering if like, and this, I know this is like a little bit niche, so maybe, but I was wondering like, is there any potential link between like the sticky walk and like edge reinforced walks? Because there it's like once you've seen an edge, you want to go to it more. Whereas here it's like you want to stay on the vertex you're on. I realize these feel pretty different, but like, is there any chance that like, if in case is there any chance that the techniques might cross apply or anything?
I actually haven't like thought of like edge reinforced graphs, so it seems that they might be similar. I'm not sure though. I'd have to think about that.
Okay,
but, yeah,
sorry.
That's interesting. Yeah.
I guess I have maybe more of a soft question for all the speakers today. This the topic of this session was analytical tools. So in all your talks, you describe very interesting open questions and sophisticated analytical tools that you used either to solve it or to make some progress on it. And maybe something kind of intriguing and is how do you find the right tool for like the questions that you're working on, and maybe another vice versa, you can ask, how do you find the right question for your given tool, right? If you have a very good tool and I have to use this tool to do something interesting. So if you can share your thoughts about that.
Okay, so I will say something about it. So the original proofs for the KKL type theorems that I mentioned use the hypercontractive inequality, and actually we try to get rid of it because it has some limitations. Use the corollary that we use there, use the degree of the function, maximal degree, and when we take a Boolean function and cut, we can truncate it at some degree, and then we might learn something about it with hypercontractivity, but we lose the Booleanity and sometimes even the bounded values of the function. So we try, and there are other works that did some proofs for this theorems that doesn't use hypercontractivity, but the tool that we use, the Log-Sobolev inequality, is very close to the hypercontractivity. It's even considered as the limit version of it when you took some parameter there. And then we actually, much effort we did is to analyze the general version of the Log-Sobolev inequality, and there used some tools that we actually use in other works and are pretty common in this area. So it was some combination of some trivial tools to use and some others that are more original.
For me, I'm always fascinated by how much we can get by just a simple tool of random restriction that, year after year, we see more results using this simple tool. And it's kind of
perhaps interfere and just make like one small remark. So there is John Bourgain, of course. And if you look at his papers in analysis of Boolean functions, it's hard to see, but they all boil down to random restrictions. Like he does them very, very cleverly, and sometimes under the hood. And but yeah, it's a very powerful technique, and like once you know how to use it and combine it with other things, the sky is the limit.
Do any of you have like particular recommendations for like particularly beautiful examples of random restrictions in the use of analysis of Boolean functions? I'm sure I should start with the current paper, of course, but any other cool applications of random restrictions in this area?
Well, like the famous examples are like the switching lemma and applications for it in proof complexity. So a good survey by Paul. There's a very beautiful survey by Paul Beam if you want to learn a little bit more about that. Probably Dor would say more stuff, or others. Feel free.
Yeah, it's tricky. So yes, so there are some early applications of it for like the problem of junta testing, which are not too complicated, but still quite clever. But after that, it sometimes gets a bit hard. Like so, you can try to prove that sort of junta theorem, saying that if your Fourier tail is decaying quickly, then your function is a junta, is close to a junta. So if you don't care too much about getting optimal parameters, it's a very nice exercise. In the sense, it's a paper to do it with random restrictions, but if you want to get the optimal thing, then you have to be Bourgain. Yeah.
That makes sense. Thanks. Oh, sorry.
Yeah, so I have another soft question. Maybe I will focus it more now on like it's maybe relevant to Tselil, Dor, and Omri, but feel free to answer as well. So it seems that some of you developed like a new definition or a new conjecture. When doing it, how do you know that this is the right one? How do you you have so many choices when you make a new definition? So what made you choose this definition or this conjecture versus any other choice?
So for us, we saw what didn't work, and we guessed. So the analytic results that we developed, we kind of developed some of them already from a combinatorial perspective. So we had some guesses what should work and what shouldn't. And I mean, surprisingly, things worked. I'm not sure why relatively early guesses already worked, but we just tried several types of definitions and constructions, and they didn't work. And then one of them did. Yes, it's a matter of trial and error, I guess.
Right, and also like in your talk, you sort of talk about these failed attempts that sort of lead you to the next one. So that's a good approach. Yeah, and maybe it's still.
Yeah, I guess in our case with the Strongish planted Clique hypothesis, the choice of the conjecture was of the hypothesis is kind of suggested by the current frontier of algorithms. When we started the work, we were trying to get reductions between different distributional problems. So we wanted to look at like whether we could get a reduction from planted Clique to a average case version of densest case subgraph. And there, like, we were willing to be more flexible about, kind of how like the running time of one of them translates to the running time of the other. So we weren't married to, n to the little log n, but we thought like whatever correspondence we could get was interesting. But then we realized that this very simple reduction, if you start with Strongish planted Clique hypothesis, gives tight inapproximability results for dense case subgraphs. So we were happy with that.
So the order is not necessarily the order which we presented, more or less. Maybe you have the reduction first and then the conjecture later.
Yeah.
And also, like, another question that I saved from earlier about your talk is, I'm not super familiar with everything in this area, but I know that there are some reductions on like hardest of approximation of cadence subgraph from Ceph, right? So the question is, what's like, how would you compare the two results, like in terms of regimes of parameters and in terms of, is one implies the other, or?
Okay, so here I'm a little bit worried that I'll say something incorrect, but I can tell you my what I recall. So the results that start from Seth, they managed to get an approximability where this term k can be almost polynomial in n. So right, and we don't get to take our k that large. So our k's are at most polylogarithmic. Right, so that's the main kind of difference, and there's a number of different there's a different densest K subgraph reduction that by Alon et al. That uses almost the same reduction, but they don't do a randomized reduction. They take kind of all of the sets, and then they're able to get hardness for a different regime of densest K subgraph. So yeah, so it's sort of like the choices that you make in the reduction really. Or in the starting problem, really determine kind of which regime you can handle. Yeah.
Thanks.
Hi. I had a kind of a discussion query for the panel. So I was thinking if these excellent results can be extended or scaled by using some sort of a function approximation for a multi-layered or a hierarchical graphical structure. So how will that work? Maybe in a form of multi-layered neural networks, such that these results can be well bounded on some sort of a approximation problems with respect to large data sets. So I was thinking more in terms of machine learning here.
Can you maybe focus your question for which speaker are you referring it, or is it just a general?
It's just a discussion query for all the five speakers. So if I was thinking, what were their thoughts with respect to the scalability and throwing in some approximations for making their results. How do I say it? Extend to multiple domains, or specifically easily generalized. So I hope I'm clear.
Yeah, I'm not sure that I understood exactly. If you can give an example for maybe
with respect
related
to
one of them.
Yeah, with respect to suppose having multi-layers of the same uh, uh, approximations with respect to suppose convergence or uh, uh, inference. So in both the context, can these handcrafted uh, uh, how do I say it? Hard bounded problems can be scaled with respect to having large data sets and can be easily generalized. So that's what I was thinking from a general machine learning perspective.
Okay, I didn't understand your question because I'm not expert in machine learning, but maybe I have some answer for you. Our work, you actually can extend it to bounded functions.
Mhm.
So maybe if this type of extension interests you, this is actually what we prove because we need it for some for our main proof, but maybe it helps you.
I got that, but I was thinking with respect to the extension. Okay. Suppose if I put it naively, if I want to have a subgraph here which can solve those queries or those problems in a more efficient manner, I have some sort of a causal relationship with respect to a hierarchical graphical structure. So I was thinking more in terms of that, making those small algorithms combined together to solve a bigger problem. More in the case of machine learning, or if you take this or extend this into a reinforcement learning context. So I was thinking more in terms of that. Okay, then fine.
I think you are way ahead of us. I mean, you see connections that we are still to see probably, but
yeah.
But
Thanks.
some of these questions are relevant to very big question like P versus NP and stuff like that. So that's definitely okay. Any more questions?
A quick question for Esty. Do your techniques give you Bourgain's Junta theorem, or is there any hope of getting?
Excuse me?
Bourgain's Junta theorem?
What do you ask?
Oh, like you use random restrictions and Log-Sobolev inequality to get KKL, Friedgut, and Talagrand, right? And like another Junta theorem is Bourgain's Junta theorem.
Yeah.
Is there any hope to sort of use your techniques to get Bourgain's theorem?
Yes. Actually, I'm not sure it's not already done.
Okay, interesting.
Yes, actually, this is the purpose of this talk, to find more applications to this technique.
Okay, cool. Yeah. Thanks.
Okay, you're welcome.
Right. Thank you for sticking around. I guess we are now well into our lunch break, so I'll let you take a break and maybe eat dinner or lunch depending on which continent you are. And see you later. Thank you.